Hello! In this video, we're going to talk about using the technique of separability to solve ordinary differential equations. So a differential equation that looks of the form, say dy dx is g of x over f of y, it can also be multiplied, it doesn't have to be divided, is called separable. And it can be solved by moving the variables related to x and y to opposite sides of the equation and then integrating. So in this example, I move the f of y to the left, and I move dx to the right in the usual abuse of calculus that we do, and then we integrate both sides. Be sure to include an arbitrary constant when we're doing that indefinite integral. And then we solve for the solution y of x, and that'll give us the general solution to the differential equation. This makes a lot more sense when we talk about an example, so let's look at an example. Our example is dy dx is equal to 6 times x. This is definitely of the separable form. In fact, there's no y's anywhere, and so all we have to do is move the dx over to the right-hand side. And then we're going to do an indefinite integral on both sides. On the left-hand side, we do an indefinite integral over dy, and on the right-hand side, we do an indefinite integral over dx. And then, of course, we have that arbitrary constant that we put in, c here. If you do those integrals on the left and the right-hand side, on the left-hand side, you just get y. On the right-hand side, you get 3x squared, and that's arbitrary constant still hanging around. And so the solution is actually y is now a function of x, and it's equal to 3x squared plus c. And you can check this by putting it back into the differential equation, and you'll get the same thing back again. Let's look at another example. So let's look at the example dy dx is equal to xy squared. This is an important example because this is actually a nonlinear first-order differential equation. And oftentimes nonlinear differential equations are really hard to solve, but this one's not too bad because it's separable, and we can use the technique of separability. Take a minute on your own, pause the video, and see if you can solve this using separability, and then come back. Okay, hopefully you're back. So let's solve this using separability. Let's move the y's to the left-hand side and the x's to the right-hand side. So I have dy over y squared is equal to x times dx. And then I'm going to do the indefinite integral on both sides. On the left-hand side, I have an indefinite integral of dy over y squared. And on the right-hand side, I have an indefinite integral over x dx plus c, that arbitrary constant. When I do the integrals on the left-hand side, I get minus 1 over y. On the right-hand side, I get 1/2 x squared, and then there's still a plus c floating around over there. And so now I can solve for y of x. And so I have to do a bit of algebra in order to solve for y of x. Fortunately, in this case, the algebra is not too bad. Sometimes that algebra can be a little nasty. But ultimately, I find here my solution is y of x is equal to minus 1 over 1/2 x squared plus c. This has an arbitrary constant floating around, and so this is a general solution. Notice that the plus c has to be down in the denominator with the 1/2 x squared, because that's how it showed up when we solved the separable differential equation. We can't pull the plus c out of the fraction and then put it at the end. That ends up not being a solution to this differential equation. Okay, so hopefully you have a better idea of how to use the technique of separability to solve differential equations.